Look at a traditional central air handling unit operating inside a commercial building. The sheer spatial footprint is massive, requiring a sprawling ductwork network just to move conditioned air from a central plant to individual rooms. These centralized systems offer exact psychrometric control, the ability to finely tune temperature and humidity in one primary location. But that precision demands enormous structural accommodations, eating up valuable architectural volume. To reclaim that space, engineers turn to decentralized unitary systems. Unitary equipment takes factory-matched direct expansion, or DX, refrigeration loops and shifts them directly into the local building zones. The mechanical work happens right where the cooling is needed. But there is a trade-off. A central plant can easily adapt its flow to shifting loads. Unitary systems rely on rigid, fixed cooling capacities. This fixed capacity creates a primary engineering challenge: the sudden inability to independently manage latent heat, or humidity, in the zone without overcooling the air. It also creates a secondary challenge: efficiently sourcing and sinking heat from a localized, decentralized node when you no longer have a central boiler or cooling tower to rely on. To solve these problems, decentralized architecture had to evolve. We can map this trajectory by tracking the progression from rigid, isolated PTACs to fluid, variable refrigerant flow networks, and finally to ground-coupled heat pumps. Decentralizing a building's HVAC means trading bulky spatial infrastructure for complex zone-level thermodynamic accounting. We start with this schematic of a standard window unit, which establishes the baseline mechanical architecture of a packaged direct expansion loop. Notice the strict separation of the indoor evaporator airflow and the outdoor condenser airflow. This exact fixed loop logic scales directly into commercial packaged terminal air conditioners, or PTACs, applied across multi-zone buildings. As shown here, the cooling system and heat section combine within a rigid, self-contained chassis fitting squarely into a single wall sleeve. Because the airflow rates and coil geometries inside that chassis are permanently set at the factory, their performance envelope is entirely locked. The mathematical representation of this rigid envelope is the sensible heat ratio, or SHR. For typical unitary commercial equipment, this ratio is locked at roughly 0.75. This animated psychrometric chart shows how a standard 36,000 BTU per hour load is broken down. The total load resolves into a horizontal vector of 27,000 BTU per hour of sensible cooling and a vertical vector of 9,000 BTU per hour of latent cooling, permanently locking the SHR slope at 0.75. The failure mode emerges when occupancy suddenly spikes, driving up the latent moisture load. The PTAC cannot dehumidify that extra moisture without also drastically overcooling the sensible room temperature, pulling the system completely out of the required comfort zone. To bridge this gap, engineers deploy a dedicated outdoor air system, or DOAS, which serves as the mandatory counterpart to these unitary systems. Rather than forcing the local PTAC to handle the excess moisture, the DOAS specifically intercepts and strips the latent load from the incoming outdoor ventilation air before it ever reaches the zone. Because isolated unitary systems are rigidly bound to sensible temperature control, they fail structurally unless paired with a DOAS to manage the latent DAP. To move past the limitations of rigid on-off equipment, decentralized architecture evolved into variable refrigerant flow, or VRF, networks. The core of a VRF system is an outdoor variable speed compressor. Instead of running at a fixed output, it actively modulates its frequency based on real-time suction pressure and changing mass flow demands. Look at this schematic linking the central compressor to multiple indoor fan coil units. At each indoor unit, an electronic expansion valve, or EEV, precisely throttles the refrigerant flow to maintain specific local temperature set points. By expanding this piping into a three-pipe system, utilizing distinct liquid, suction, and hot gas lines, VRF systems can deliver simultaneous heating and cooling to different zones without requiring bulky, centralized water loops. A branch selector box acts as the system's traffic controller. It routes high-pressure, high-temperature hot gas to a perimeter zone that requires heating, while simultaneously routing liquid refrigerant to an interior core zone that requires cooling. The thermodynamic efficiency here is striking. The system is extracting heat from the warm interior core of the building and moving it directly to the cold perimeter, completely bypassing the outdoor unit. Depending on the specific design, 30 or more of these direct expansion fan coils can be networked to a single condensing section, providing deep modularity across a large commercial floor plan. VRF systems elevate unitary architecture from localized isolation into a dynamic, interconnected thermal economy. Heating inside these advanced unitary and VRF systems is achieved by running the Rankine cycle in reverse, operating the equipment as an applied heat pump. In this technical schematic, focus on the four-way reversing valve assembly at the top center. This valve dictates the directional flow shift between the compressor and the coils, literally swapping the roles of the evaporator and the condenser in the refrigerant circuit. However, a heat pump's efficiency is absolutely bound by the physical medium of its heat source, which for most unitary systems is ambient outdoor air. This graph illustrates the thermodynamic penalty of using an air source system. As the ambient temperature falls, the building's heating load steadily rises. Yet exactly when that heating demand peaks, the air source heat pump's capacity steeply drops off. The critical failure threshold occurs when the surface temperature of the outdoor coil drops to 32 degrees Fahrenheit or below. If there is high ambient humidity, atmospheric moisture instantly phases into solid frost directly on the metallic fins. That frost acts as an insulator, physically choking off heat transfer. The system is then forced to temporarily reverse itself again, entering an energy-intensive hot gas defrost cycle just to clear the coil. Engineers mitigate this through specific coil design. They might widen the fin spacing to 4 or 5 fins per inch to delay frost accumulation, or tighten it to between 10 and 20 fins per inch if the system is equipped with highly aggressive hot gas defrost logic. While air source heat pumps are highly accessible and easy to install, they remain thermodynamically volatile and are strictly bound by the limits of atmospheric moisture. To bypass the volatility of the atmosphere, engineers utilize ground-coupled heat pumps. Note the buried ground loop interacting directly with the water-to-refrigerant heat exchanger. A common architecture for this is the deep well system. It features a high-pressure plastic U-tube inserted several hundred feet deep into the earth and encased in a specialized heat transfer grout. The absolute capacity of this ground loop is dictated by a core metric known as thermal diffusivity. This formula defines thermal diffusivity as the ratio of the soil's thermal conductivity divided by the product of its density and specific heat. The moisture content of the soil drastically swings this equation. Wet clay diffuses heat outward rapidly, pulling energy away from the pipe, while dry, sandy soil acts as an insulator, trapping the heat in place. The long-term risk of a ground loop lies in this exact math. If thermal diffusivity is miscalculated, the heat pump will thermally saturate the well field over consecutive seasons, crippling the system's efficiency. Ground loops offer a stable, frost-free thermal baseline, but they demand unforgiving, precise geological mathematics upfront to function effectively. Now we can synthesize these elements into a unified model of a high-efficiency commercial building. This wireframe animation shows a DOAS unit dropping onto the roof. It intercepts and strips the latent moisture loads from the outdoor air, sending dry ventilation down to the floors through blue shafts. Next, we layer in the VRF network to handle the sensible mass flow. Notice how it dynamically routes excess heat from the sunny south-facing facade directly to the shaded north-facing zones. Finally, the entire network is anchored deep into the earth by a ground-coupled well field, establishing a highly stable thermal sink. Removing a massive central air handling plant does not simplify a building's mechanical profile. It distributes that thermodynamic complexity directly out into the individual zones. By mastering the local physics of latent heat, variable mass flow, and thermal diffusivity, engineers can dismantle the traditional central plant, delivering thermodynamic efficiency exactly where it is needed.